Hello and welcome to Technical Toolboxes webinar today, HDD, Designing for Constructability and Success, with the well-renowned David Willoughby. We also have our in-house SME, Joe Pikas, on with us to later showcase the newest AI enhancements to the HDD Power Tool. My name is Kesley Price, and I work here at TT. We will get started here shortly, but first a couple of logistical details I need to cover. If you have any questions on what we're covering throughout the presentation, please, in the top right of your GoToWebinar interface, you'll see a chat box or questions tab in the top right of your screen. Please send us any questions you may have throughout the webinar, and we will do our best to cover all those questions we receive at the end of the session. We will also be sending a copy of the webinar recording to anyone who registered and attended. Also, those who couldn't make it will get an email with the webinar recording within the next couple of days. And you'll also be able to see this on our Technical Toolboxes YouTube channel. Next slide, please. So speaking of the renowned David Willoughby, a little bit about him. He has over 40 years of experience in HDD design and construction, and he is the author of Horizontal Directional Drilling. Many of you have either probably studied this or used this as a reference for something you're doing HDD related at some point in your career or during college. His contact information is down there at the bottom if you need to reach out to him, but at the end of the presentation, we will also have contact information. We are excited to have Willoughby on here, and everyone seems to love his presentations. So speaking of which, what we're going to be covering today for HDD related designing for constructability and success. First, we're going to cover the root causes of HDD project failures. Then we will move on to part 2, designing for real world conditions with HDD Power Tool. Then we will cover the constructability review. And then, like I mentioned, Joe Pikas will join us to give us an overview of our latest AI enhancements within the Pipeline Hub for Piper Insights to help you validate your calculations related to HDD. And then at the end, we will cover the live Q&A. So all your questions you submit, we will have David Willoughby and Joe Pikas on here to answer all of those live for you. Next, we have a quick poll question. So to get us started, we wanted to poll the audience at the beginning of this webinar to see where you stand. The poll we will show you now, it will be up here for a minute to help us kind of gauge how you are currently involved with HDD projects and what brought you here today to the webinar. So are you currently involved in HDD project planning or design? And then kind of giving us your input there will help us kind of guide how we kind of tailor these going forward. So please take a second to answer that. We'll give that another 30 seconds and then we'll move on to the presentation. Again, thank you for being here today. We really appreciate your attendance. As we move through the presentation, please submit your questions in the top right tab for the questions, and we will cover those. The more the merrier, and if we're not able to answer within a timely fashion on this webinar, we will email you with follow-up answers. All right, let's get started. David, I will turn it over to you, sir.
All right, thank you, Kesley. I'd like to welcome everyone to today's webinar. And she gave you a good topic of what we're going to try to cover today. Of course, we can only cover it in so much depth in the amount of time we have, but what I tried to do today was put together some of the material that I get a lot of questions on from people in the different classes that I teach, and just talking to people who have issues with their HDD. So I kind of took some of the ones that I hear about the most questions about, and put them in the presentation. So we're going to focus on how to improve your odds, and also how to make drilling a successful endeavor. Now, one thing that I tell you up front, when we say we have a successful HDD, that includes more than just successfully pulling a product pipe back through a hole. Now, that's certainly part of it. We've got to do that. But we've also got to do it for a reasonable cost, right? We've got to keep our costs within reason. We got to have minimal impact, especially environmental impact, on the area that we're working in. And we've also got to do it in a manner that allows a contractor to make a fair profit. I know a lot of us hate to hear that, but believe me, if contractors don't make fair profit, they're not continue to do the work. So when I go through a design, I want to do one that gives the owner a good value for a dollar, but also make sure the contractor has a chance to make a fair profit on what he does. So when we go about doing that, we design the drill path. We have to consider all of these things I just mentioned, and we also have to consider all the information that we have about the crossing area, what we're actually crossing. These include the physical limitations of the site. These could be limitations on where we can put our equipment. It could be roadways, it could be railways, water bodies, whatever is a physical limitation to where you can lay out. That's always key. And a lot of times that's one of the things you can kind of look at the easiest using Google Map or whatever type GIS system you have. You kind of look at what the existing infrastructure and what's in the area and kind of pull out those physical type limitations. We also got to look at geotechnical. That's the subsurface, and again, make sure that we can do drilling in the kind of soils that we're going to be in. Environmental, like I said, is a big issue. We got to make sure we have minimal environmental impact. That includes fish, wildlife, vegetation, cultural, historical, whatever you might be in that area you're working in. But that's always a key to us. And then, of course, hydrological information as well. So we're going to consider all those into our design. Again, make sure we have minimal impact. And again, contractor can make a fair profit. So today, again, we're going to look at some of the things that we can do to kind of improve our odds to having a successful project. Again, understanding that when I say success, I mean a lot more than just pulling a pipe back through the hole. Now, every drill is a little bit different. I've drilled thousands or designed thousands of these, and probably no two are exactly alike, but they're all a little bit different. They all require some level of surface and subsurface investigation. Many of them require very extensive surface and subsurface investigation, depending on the crossing that you're at, the environment that you're in, the terrain that you're in. But we have to look at both the surface conditions and the subsurface and come up with the feasibility of an HD project. And again, and we use all that data to help us with our preparation for the project, our planning, our permitting, and of course our design, and then at the end of the day, our construction. Now, the level of that effort that we have to use is affected by a lot of factors: site conditions, soil formations, terrain, utilities, equipment restraints. All those tie into it. Now, remember, when you do a drill, any drill you do, whether you're crossing a small city street with a mini rig, or if you're crossing the Mississippi River with a maxi rig, all of them go through the same steps. These conditions are important for every one of them. It's just sometimes they get more critical depending on the nature of the crossing that you're doing, depending on the site conditions that you're at, depending on the kind of soil that you're in, the terrain you're in, and of course other infrastructure in the area. So we have to determine the level of engineering effort is really going to be unique from project to project. You don't want to engineer it too little, but you don't want to engineer it too much and just waste a lot of money either. So that comes with experience. But every drill you do, these things are going to be important. It's just a lot easier. If I go up here, if you look at this drawing up here in the right, you look down that road. If I'm doing a site survey there, that's very straightforward. I'm in the shoulder of a road. I got the roadway going there. Main thing there is going to be identifying utilities and things of that nature, right? So it's pretty straightforward. If you look at that one down at the bottom down there, you see the drill rig there, and you see all that timber matting down there. That was actually in a golf course. That was about almost a 6,000-foot drill. So the site conditions, the terrain, everything was a lot different there than it was the one up above. So the level of effort on this one at the bottom was a lot more level of effort as far as design and engineering than that one above. So it'll vary from project to project. Just keep that in mind. Now, regardless of the upfront engineering, it's not unusual for that bore path to change during construction. The soil conditions aren't always what you expect. Things can happen. A contractor can't steer quite as aggressive as you want him to. He couldn't make certain points. And again, that can make things change. So it's not original for the design to change during construction. So that's why it's so important that you have a good idea of the site conditions, and what you can and can't do. So when you're going to select a crossing location, you got to make sure you always consider constructability. I call it means and methods. If you're working with a contractor, that's his means and methods. Now you got to consider those. I didn't say you determine them. Means and methods are in the contractor's world. I'm sure I probably got some contractors in here, but a lot of you are probably engineering and design. So You don't have to determine the means and methods. The contractor's going to do that, but you certainly have to consider those in your design. And so you have to consider the means and methods. You have to consider the alignment that you're crossing, what you're actually crossing, the obstacles and whatnot. And of course, access to the site is very important as well. And when you look at that alignment, you got to make sure that you've got adequate room for your entry and exit pads. Again, your access routes. On the rig side, you got room for your rig and all the equipment that goes with that. On the pullback side, you got room for your pipe string, fabrication, testing, and all things of that nature. So you're going to go through those and make sure you have those. It would surprise you if I tell you how many projects I've been involved on where there was a problem and a big issue because the designers didn't give the contractor adequate space to do what he had to do. So always you make sure that you pay attention to those layout areas and that required workspace. And what you want to make sure is you see those two bullets at the bottom. The big thing there is flexibility. When you're doing a crossing, always look for flexibility because, like I said, things change a lot of times during construction. And the more flexibility we have, the more chance we have of being successful at the end of the day. Even if it don't look exactly what we designed, we can still wind up with a successful project. Okay, and that's what we try to do. If this fails, what next? Can I change my drill points? Can I change my exit point? Do I have to pull back out and re-drill a complete pilot hole? Do I need to change from directional drilling to auger bore? Just look at flexibility, and that's what you want to have. One of the root causes of all the failures that I've seen. Again, failures when the project is not completed. You don't complete the project. And one of the big things I've seen when you have project failure is a lack of flexibility in the original design. Now, I'll be honest with you, I've done projects where the original design was the only way we could see to make it work. And we all knew if that failed, that was going to be a failed project. So sometimes you'll get in that situation, but at least you'll go into the drill knowing you're in that situation. Okay. But if you can find some flexible alternatives, that's exactly what you want to try to do. That will help reduce those project failures. The terrain of the location have a big impact on the risk of failure and have a big impact on both your actual bore path you design and also the feasibility of an HDD. Now, I don't have time today to get into all the things we look at in feasibility, but that's a very important part of our original planning and design. When we start to do a drill, the first thing we look at is feasibility. And if you don't do a good feasibility analysis up front, you're really going to increase your risk of having a project failure. So I certainly encourage you to pay attention to that feasibility step. But a lot of time, one of the problems I see quite often is the designers and engineers do not pay attention to the constructability of a project. When they look at a project, it kind of becomes an exercise in geometry. If I can do my entry angle going in and my angle coming out, and I can put my point of curvatures and point of tangents, and I can negotiate certain things. That's what they consider a design. But all those are important in the design. Don't get me wrong, but you can't look at those in a vacuum. You always have to consider those with constructability. So remember, when you're designing a drill and you're doing the negotiating obstacles and doing the geometry part of it, always keep in your mind, I can draw it, but can a contractor build it? That's a very important item. You can draw anything, but a contractor can't build anything, okay? So what we do when we select that crossing method, we kind of strike a balance between what we want to do, what our primary route is, look at various alternatives and various things we can do, and then we'll come up with the most practical solution in what we're going to do, okay? And what we usually prefer is a method that's technically feasible. That's the first thing. I don't care what you do. If it's not technically feasible, if a competent contractor can't do it with today's means and methods, then you want to look at something else, okay? But so normally we'll do HDD when it's going to be cost effective, it's technically feasible, and we can provide environmental protection. Now, the location of the entry and exit pits are the direction of the pilot hole, direction of reaming and pullback. All those are established, based on the site surface conditions. And once we lay it out, and a couple of things to remember, we talk about project failures. When you're choosing where you're going to put the drill rig, where you're going to pull back, and what you're going to do. Now, of course, you're going to look at the surface and see where that stuff will fit. That's always important. But yes, assuming you've done that, a couple of things to remember. when you choose the relative locations of the entry and exit pits, remember that steering precision and drilling effectiveness are best the closer you are to the rig. Okay, so the closer you are to that rig, the more accurate you're going to be with your steering, and the better the contractor can manage that hole. So whenever it's possible, you want to have your entry point where your drill rig is located close to any anticipated adverse surface conditions or another obstacle down the hole. If you look at this one right here, you see the rig right here, and you see it's going under a railroad track, and then you got a water body right here. You can see how they actually dug a pit to get this rig down deep enough because we had to get deep quick to get under that railroad track. Okay, but again, the closer we are there, the more accurate we're going to be with our drilling. So we'll know we've got the depth we're trying to get, the distance from the railroad track, and also the better we can maintain that drill hole. So just keep that in mind. The closer to the rig, the better you are for those adverse conditions. Another thing we see a lot of time cause product failures is not paying attention to soil conditions. I'll give you an example right here on steering. Now steering, the way we steer our bits down the hole is we use the passive resistance of the soil between the drill bit and the soil to deflect that drill bit and go off in the direction that the contractor wants to steer in. So if you have very soft formations, steering, and especially sharp bends, aggressive steering, are not usually possible. And you see right here on this chart here, you see the one highlighted is fine grained soils, and you see this right here is fine grained soils here. This is coarse grain, but you see right here, this tells you where you can have a poor steering capability based on the kind of soils you're in. And so if a contractor's drilling in that kind of soil, even though you can draw it, if you have him steering in a soil that says less than 10 or less than 15, depending on what kind of soil you're in, he has a very hard time steering in that kind of soil. In fact, sometimes he can't steer at all. So no matter what you draw, he can't do it. So a lot of time you'll see something like this. If you look right here, you see this red line right here is our bore path right here. And that was a preliminary bore path. This is a real project, by the way. I cut it out from that was the preliminary bore path. Now, once we got the geotech results back, you can see between these red lines right here, the soil condition, the blow counts, the stiffness of that soil was so low that we didn't think a contractor could steer within that zone. Now, if you look right here's the point of curvature here, and here's the point of curvature right here. So again, it was drawn that way, but a contractor probably couldn't build it that way. So if you went out to build this and didn't do it, what would wind up happening? The contractor couldn't make that point of curvature, so he would keep going straight at whatever this angle is, 10-degree angle. He would keep going straight till he got down here in some good soil, and he would start steering down here, and that would make your whole drill wind up something like that. So if you change it during design, you would actually move that point of curvature down there, so you know where your bore path's going to be. Now, if you don't do that, if he can't steer, and he winds up, a lot of times you wind up making this drill a lot longer than it was going to be till he got down that good soil where he can steer. So again, always pay attention to your soil conditions. We can draw it. The first design right here negotiated every obstacle with no problem. But again, there's something a contractor couldn't build. So always maintain constructability. Another thing, like I told you, a lot of times, once the obstacles are defined, once the surface conditions are defined, then we can go pretty much a straightforward exercise in geometry. Once you've identified all the obstacles, and I say that plural because most drills have more than one obstacle. So you have those defined, you've got your depths under those, everything defined, you look at your soil conditions, then you can look at the geometry and do a straightforward geometry exercise to negotiate all that. And when you do that geometry, you got to consider your setbacks, your all the existing surface features, other utilities, no drill zones. This right here would be a no drill zone. These two red lines you saw there, that would be a no drill zone. Of course, there are other facilities. One thing that we see quite often, remember, if you're drilling under something and you have a requirement to maintain a certain distance from another utility, for example, make sure you consider the diameter of the reamer when you're doing your offset. Because let's say right here, remember when you draw that dashed line on a piece of paper, that's your pilot hole, and that's what the contractor's drilling to, is that pilot hole. So if there was a pipeline right here, and your permit said you had to maintain 10 feet from that pipeline separation. Well, if you maintain that during the pilot hole, and then you go back and ream it out, and you're reaming it out, a 2 foot bigger. So now when you go through, now that utility's right here, instead of being you're 10 feet away you had here, now right here, maybe you only got 6 feet. Maybe you got 5 feet. So you're not maintaining that clearance. So make sure you always consider the diameter of the reamer or the product pipe, whatever's the biggest part of that hole, when you're considering your offset requirements. It's just another example right here. You can see right here, right here is 48-inch sanitary sewer, and you can see that pipe there is 10 foot below that sewer. Again, that dashed line is the pilot hole. Now, I think this was if I remember right, 8-inch pipes. So you're gonna probably be looking at around a 14-inch reamed hole. So again, if you have 10 foot around the pilot, you're gonna wind up with something less. And that spec did call for a 10 foot clearance. So just keep that in mind when you're doing your design. Always pay attention to how whole that's going to be, and any requirements to have a distance. That's going to be whatever the largest thing is that goes through that hole. Keep that far away. Another thing I talked a little bit about is a little bit about inadvertent returns and frac outs. Now, one thing, depth of cover. For years, people used a lot of rules of thumbs for depth of cover for drilling. They wanted to be so much of depth under a highway, so much under a water body, so much under another utility, things of that nature. We've gone way past that today. The depth of cover of any obstacle, whether it's a surface or another utility, should be governed by the definition of that obstacle. Okay, and there's a lot of things go into it. The surface conditions that you're in, what kind of soil you're in, the drilling equipment, the mud pressure, elevation differences, all that can go into play. But the maximum depth of cover is established by calculations we do for the maximum allowable borehole pressures. How much pressure will that formation hold before you have what you see on the right over here. And we compare that to the pressures that we need to have to keep that mud flowing in the hole. Remember, the mud's got to flow. We got to keep it moving in the hole. So that requires a certain amount of head. So we just got to make sure that the head in the hole doesn't exceed that allowable pressure in that hole. Now, in the case where the reasonable drilling fluid pressures that we put it in the rig and down the pipe, when that exceeds the allowable drilling pressure, then we have to go deeper. That's usually what we'll do, because that'll increase the maximum drilling pressure, maximum allowable drilling pressure as you get deeper. Now, just remember, inadvertent returns, any mud that comes back to the surface is an inadvertent return, because we don't want it to come back. It's back there, okay? It's not really a hazardous issue. Your drilling mud is pretty much water with somewhere between 2 and 4% bentonite mud. That's all. It might have a few additives, but there's nothing that's toxic in our drilling mud. The only time I've ever seen toxic drilling mud in HDD is when we pick up something down the hole. You go by an underground storage tank or something like that that's been leaking, and you pick up something like that. But we don't put anything toxic down the hole. It's probably the best way to say that. Okay. But we still have to look at the risk of those inadvertent returns, and we want to reduce those. Now, you notice I don't say eliminate there. I say reduce, because you can never eliminate this. But we want to reduce the risk of those returns by having a good design and by having a contractor use good practices. You need them both. If you don't have a good design, and you can have the best contractor in the world and he'll have the inadvertent returns. You can have a good design, but if you have a poor contractor who uses poor practices, you can have an inadvertent return. So it takes both, okay? Now, one thing, remember, all inadvertent returns are not frac outs. Some of them are, some of them aren't. You see this on the right here? You see that fire hydrant? In a case like that, the mud loves to follow the path of least resistance. So you'll see this all the time, where the mud will get into a utility trench, like a water pipeline. That's a lower resistance flow path than the rest of the soil. It'll run down that trench and come out around that fire hydrant, something like that. So that's an inadvertent return. You didn't frac that out, okay? So a lot of those are caused by fissures in the soil. You can have like cracks in the rock, things of that nature. You can be around other utilities, piers, piles, gravel, things of that nature. Now, when we have a hydrofracture, that is when we put too much pressure in the hole. Every soil formation will hold a certain amount of pressure, okay? And we call that a pressure gradient within that hole. Well, hydrofracture occurs when the pressure gradient in the borehole exceeds the formation pressure gradient, okay? So if I got more pressure in that hole than the formation will stand, that's when I'll have a frac out or hydrofracture, right? And again, when you have that, the soil what it does, it fractures the soil around it, creates that fracture in the soil, and the mud will flow up through it. Now that's a soil model. We model that using the cavity expansion model. That's a soil model. We don't model this for rock. We don't put enough pressure down the hole in HDD to fracture rock. Now we do have inadvertent returns in rock because it'll flow up through the natural cracks in the rock and the fissures and things like that. They're already there. So you will have inadvertent return in rock, but you'll not have hydrofracture in rock, not during HDD anyway. So again, we'll use that cavity expansion model to model the likelihood of having a hydrofracture. Again, this has been around since about the late 80s, verified by sources like the Army Corps of Engineers. It's a good model. It's reliable. It's like any other model. The better you are at loading the model and using it, the more accurate the model is. A couple of things that people have problems when they use the cavity expansion model is loading the variables. There's a lot of soil data that goes into the model, and the more experienced you are, knowledgeable you are, how to load the model based on the various soil conditions, the better results you're going to get from the model. Okay. Now, and sometimes we just don't know. You imagine when you're drilling that hole, you're going to go through a lot of different kind of soil conditions. And wherever we do our geotechnical investigation and whatnot, we can get an idea of what soils are down there, but we still can go through places where there's another kind of soil that we didn't know about that won't hold as much pressure as we thought it would. That's why I say we always model the risk of that. We can reduce the risk. We never eliminate it because we never know what we're drilling in. This right here is a good example of that. That one area you see that mud coming up was an area that the soil was different cohesion than the rest of that road. That's why you don't see frac out anywhere else. It just came out right there. And those things can happen to you, okay? But when you have the input variables, there's several things we look at. A big thing is the shear modulus of the soil. That has a big impact on how much pressure that soil will hold, okay? So there's a strong correlation between that shear modulus and the maximum allowable pressure. As the shear modulus increases, the value of the maximum allowable pressure goes up as well. They'll go up together, okay? Now, if you get this from a geotechnical report, that's great. A lot of people don't, and they'll get it from charts and tables. There's plenty of places to get it. This right here is the Army Corps Engineering Manual. But you see this value here for the modulus, the elastic modulus. You see the big range. Soil for any given soil type, there can be a big range of a modulus that you can have. So again, remember, I said the higher the modulus, the more pressure. So if you want to be conservative, you always pick the lower number on this chart right here. Always pick the lower number because that elastic modulus goes in this calculation right here, and that calculates the actual shear modulus that you use in your cavity expansion model. So a lot of people have a problem because they'll pick like a number way up here to do the calculation because it makes them hold more pressure. That's good if that's what you actually see. But if you're in a lower modulus, then you're going to have problems even though your calculations don't show that. So again, there's a wide range of the shear modulus, so it can have a big impact. So just pay attention. The best way to get that is to have your geotech firm do it for each test hole and give you the values of the actual shear modulus right here. Another thing that throws a lot of people off is the impact of groundwater. A lot of people think when I got groundwater above my drill, that groundwater is going to counterbalance my drilling fluid pressures. That's not the case, okay? The groundwater level has a big impact on what we call the effective stress, the initial effective stress of that soil. That's how much pressure that soil holds. So the ground level has an impact on that. And the effective stress has a big impact on the allowable pressure. The problem is, again, the effective stress is what we're really looking at. And the effective stress decreases, oops, excuse me here. The effective stress decreases as the groundwater increases, okay? So as the groundwater increases, that maximum allowable pressure is going to actually decrease. So you have that negative correlation, and that throws a lot of people off. Now, this is groundwater; it's not standing water. If you got water above the ground, like you're going under a river or a lake or something, that water does help counterbalance some of those. But the groundwater actually is a limiting factor, not a help. So a lot of people overlook that as well. Now, as you're going through soils of different material, you'll go through different layers, and the soil properties we load into the model. Of years ago, everybody used to just put one factor in there, and they would pick the factor that was closest to the pipe. So this table right here is different strata of soil. So this strata right here is the one closest to the pipe. So for each of these things, these go to the model: friction angle of the soil, cohesion, the weight of the soil, and shear modulus. So what everybody used to do is just pick the one closest to the pipe, and that's what they would use in their calculation. Okay, that works, but again, it's not as accurate as you do some of the modeling that we do now. Okay, so what we do now is we'll calculate the official effective stress for each of these layers, and then we'll add those together to get the total effective stress that we're using in our calculation, which give you a lot more accurate calculation. Okay. Again, you can use the layer of soil around the borehole. It does have the greatest influence, but it won't be quite as accurate. Another method people use a lot of time is the average weight of the soil layers. So they'll take the soil layers and just get an average weight and put that in there instead of just using this weight right around the pipe. They'll use that average soil layer. And again, your other factors like angle, cohesion, shear modulus, normally we'll use those in what we call a weighted average. Now, we give a lot more weight to the layer around the pipe because that's going to have the biggest impact. Normally, we'll give 85% of the weight to that one layer, and then we'll give smaller layers as we go up, okay? And again, as you do that, you just get more accurate in the model. It gives you more accurate results of what you don't expect to see out in the field. Now, I cover pipeline loads and stresses in other webinars and classes. I don't really have time to get into that in detail today. Just remember, we have three primary load conditions: tension, bending, and external pressure. That's the main one we have to deal with all the time. What I do want to look at real quick in this class is what we call the elastic instability. All right. Now, steel pipe can fail by buckling or collapse when it's under the influence of that external hoop stress. And again, that can come during a drill by either the mud in the hole, if you lose the hole, the soil in the hole, anything that put that external stress, hoop stress, can cause buckling or collapse of that pipe, like you see that pipe right there. Now, when we want to reduce that risk of that happening, we look at what we call the DT ratio, diameter to wall thickness. Now, for steel pipe, you want to keep that below 60. So the diameter divided by the thickness should always be below 60. A lot of you contractors, they really get nervous if you get it anything more than 50. And because what that does, when they're bending that pipe, you get it down the hole during installation and in the hole, they have a lot more likelihood of buckling that pipe like you see right here. Okay, so I would always keep it below 60, and again, below 50 is even better. Now, you can go with a higher DT ratio. Now, just say your owner has a certain diameter and they want to go with a certain wall, and that's got a DT ratio of 75. Okay, you can use the higher ratios as long as you have do a good analysis and you have a high level of confidence in your analysis. What's going to happen during pullback. Another way we'll counter that sometimes is to put internal pressure in the pipe. If I put internal pressure in the pipe, that's going to offset that external. Okay. So again, a lot of time we'll see problems with that if you get up above 60 and you don't look real close at your overall design and how we model that analysis, you can't have that happen to you. Now, I covered this in detail in the advanced webinar. I don't have time to get into all the mathematics of it today. Here's one calculation I did want to show you. This is called the critical external pressure. Now, when that DT ratio is high, if you stay below 60, you don't have to worry about this. But if you get up, those higher DT ratios, and you want to look at the risk of that elastic instability, you can do this calculation right here. Okay. Now, the elastic instability is when a body will collapse, even though the load applied does not create stresses that exceed the yield of that pipe. So you got stress loads lower than yield, but you can still have that elastic instability based on that DT ratio, okay? And the reason that is that your calculations for stress formulas, they assume the load is perfectly centered and that the pipe is perfectly round. And that's not the case at all. So this calculation right here takes that into account. And you can see all it's based on is the modulus of the pipe, the Young's modulus, the Poisson's ratio, and that DT ratio. And that'll give you the critical external pressure before you can expect to have elastic instability of that pipe, right? All right, now we're going to change over and we're going to go into the HD Power Tool, and I want to show you a couple of things in that. Let me see here if I can get us over there. Kelsey, or I'll let you tell me. I'll make sure I go to the right place on this.
We're still seeing your slideshow right now, but
Okay, I'm trying to get there
I'll let you
now.
know when it's up. There we go.
You got my login?
Yes, sir.
Okay. All right, this right here is the HDD Power Tool. Again, I don't have time to go into this in detail. I just wanted to show you how we use some of this for our design and trying to help overcome failure. And this right here is you see right here, this is your drill bore path design. So this first tab right here is where you actually put your design. Now, the reason this looks out of sequence right here, I'm showing you a compound bend. Again, this is the 2D drawing right here. Compound bends in 3 dimensions, so you can't show it right. So that's why you see that little high point right here. Just keep that in mind. But right down here is the actual bore path. Now, remember, that comes from your design plans. The power tool is to be used once you do your design. You can take that design and go into power tool, you put it in there, and you can run your analysis as far as stresses and loads and pull loads and things of that nature. And then you can go back and make any changes you can make to your design to get the kind of stresses and loads you want to see, okay? But you start out with a design. And what I want to show you in this right here was compound bends. We get asked a lot about those. But you see right here, you got your different sections. So section A to B, so that's going A to B. And now the pipe's being pulled from left to right in this case right here. So that's A to B. So you see A to B is going down at 10 degrees, 221 feet. It's straight and down slope. Now on the section, you got straight, curved, or compound. And of course, you've got down slope, up slope, or level. So we're pulling it down, so this is going down slope. Our next point right here, this B to C is the compound bend. Now you see the little arrow right here. I'm going to hit that, and that shows the compound bend down here. So compound bend, I'm going down slope. Now my angle is 12.4. My measured length is 259. My radius is 1195. Now how did I get that? Remember, if I got a two-dimensional drawing, I'm looking at the horizontal part. I'm making a right turn in the horizontal, right? And in that right turn, I've got an 8-degree horizontal bend, and the radius of curvature in the horizontal is 2,000 feet. Okay. Now that gives me the calculated length right there. Now over here is my vertical bend. And the vertical, I've got a 9.5 degree angle, a 1492 radius. Okay. Now the power tool does a calculation for you, and it calculates the actual measured length and the radius of curvature. That's at 259 and 1195. Okay. Now, again, I teach some of the other classes how you calculate that mathematically, but the power tool does that for you. All right. And if you drew this in 3D, if you got 3D CAD, that's what you would get. If you drew the three-dimensional plane, you would get this right here. Okay. So there's your compound bend. Then you got a straight section that's level, 1,000 feet. And here we got two compound bends, but they're upslope. We're coming upslope. Okay. Again, you can kind of see the same thing. Let me open this one right here, and you get the same thing. So all you do is you take the horizontal off your plans and you take the vertical off your plans, put them in there, and the power tool will calculate the rest for you. And you'll come up right here with the calculated section of that drill, straight section. Then you come over to the next one right here, which is your pull load. This is where you put all your pipe data in. I'm going to go through all that. I don't have time. Run out of time quick here. But this is where you run your calculation, and you'll have all of your pull loads and your loads. Now, if you look right here, we passed. Maximum allowable pull force is 252,000 pounds. We're good. The total pull is 223. Now, we did pass, but that's pretty close, isn't it? So, yeah, show you how you can use power tool. You go here very quick and say, okay, no, this is a 24-inch pipe. So quite often we'll use buoyancy control for a pipe that big. So I'm going to put water in the pipe. Now, you can fill the pipe full of water, or you can put it partially full. So let's just say I'm filling it full of water, and I run my calculation. Look at two things. Here's the weight of that pipe, the submerged weight, negative 140. My pull load's 223. Now, adding water is not going to change the allowable pull. It's just going to change the pull load and the weight. Okay. So I run the calculation. Now you see it went down to, from negative means it was floating. Now it's positive 46. My pull load went down to 129. Okay. We never want to have positive pipe down the hole. We always want the pipe floating in the mud. So you wouldn't want to put that pipe 100%. So we'll say we'll go 65. Run the calculation, and see now I've got a little bit of negative in there, and I'm still good, 136 and 252. So you can play with buoyancy control very, very quickly. Let me show you one more thing. We'll move on for a round of time here. The stresses. Now I'm going to go to that last curve, this curve right here. Now look right there. You see where I got that red fail? Now, my bending stress is 25,000. My allowable bending stress is 27. So I passed my tensile stress, I passed my bending, and I passed my external hoop. But one thing about drilling, you have to look at all those stresses at the same time. We look at the combined stress. And we do that using a unity check. So right here, we're going to overstress that pipe, but because of tensile and bending, that's a fail. So again, the reason why this is a 24-inch pipe, and we got some pretty tight radiuses. So again, you can see that. You can go back in, adjust your radius, or you can look at, okay, so what if I come back here, and what if I just change my grade of pipe? Because I really want to stay with that. So I'm going to change to an X60, and I'm going to run it with that. Now I come back here to my installation stresses, and if I go back to that same spot, see, now I pass. And the reason I passed, I didn't lower my bending stress, but what I increased my allowable because of that higher smile. So again, you see how you can use a power tool to play with this and see what you want to do. Okay. Now, let me see if I can get back to where I was here. Okay. Are you back on the presentation, Kesley?
Yes, sir.
Okay. Just a couple of things real quick. I'm running out of time. I'm going to turn it over to Joe, and we won't need questions. But constructability review. The big thing about constructability, again, I talked about the surface and subsurface investigation. The big thing on this is make sure that your design is tailored to the site that you're at. One of the big problems I see all the time is people don't tailor their design to the site, and that is critical. Pay real close attention to surface features, your buildings, your roads, and areas where you don't have much soil cover, because that's where you're going to have the frac outs and whatnot. Check all your utility records. Pay real close attention to support pilings, other pipelines. That's where that mud wants to frac out into. And also pay attention to anything that has a significant steel mass, because that can cause interference with your tracking and locating equipment. Another thing I get asked all the time is about elevation differences. How much elevation can I have between my two pits? And that's going to vary from soil to soil. I've done drills where I've had 450 feet difference and no problem because I was in rock. If I'm in a certain kind of soil, it might not even like 100-foot change in elevation. So again, you have to make your design specific to that area that you're at. Okay. But what happens when you get those elevation differences, those significant differences there, you wind up and you won't have that equilibrium in there, and that creates a dry section within the hole. So, if I got my hole like this and one's up here, okay, the mud's going to settle out on that area right there. So all this area up here is going to be dry. Okay, you got a dry hole, and because you have a dry hole, that's going to be prone to the soil wanting to collapse in that hole. That's what you see right here. And as it runs run down that hole and you have a dry section, what happens? The soil will start following that dry hole down, and you'll have that sinkhole, you'll have that collapse. So but be very careful with that. Make sure you analyze that real close. Okay. Um, so again, make sure that you pay attention to those inadvertent returns. Uh, Remember, I talked about fractured rock, any coarse grain type soil, elevation differences. When you don't have enough cover, any of those can lead to those inadvertent returns. Okay. Last thing I mentioned is conductor pipe. When you have poor soil conditions at the entry and exit, which happen all the time, one of the key things that we do a lot of time is we'll use entry and exit conductor pipe. And you see it right here, this on the entry side, this on the exit side. And we'll drive those down in there, and that becomes our hole. And quite often, if you don't do that, you'll have frac outs or inverted returns at your entry and exit pit. So using that conductor pipe is something that we do quite often to control that. Okay. All right. I've just got a couple on soil here. Nothing here. I'm going to go ahead, Kelsey, and move this up to let Joe. You want to do a
Okay.
polling question? Or you want Joe to do his now?
No, so first we're gonna go to Joe. So while
Okay.
Joe's getting his screen ready to share, thank you, David, first of all. This is all great, and we have tons of questions coming in that I want to be able to cover as much as possible here at the end. So while Joe works on sharing his screen, he is going to showcase the latest AI enhancements to the HDD power tool. With Piper Insights. You saw it kind of on the side of David's screen there when he was giving you a demo, but Joe, would you give us an overview of how Piper Insights is now integrated with the HDD Power Tool?
I would be more than happy to. One of the things that David talked about, if you all remember, what was the effective submerged weight in an HDD pull through. And remember, he said it should be on the negative side. Well, how much negative? Okay. What and that's what I asked Piper. What is a typical value for the effective submerged weight in an HDD pull through? And it says approximately 11.1 pounds. And David showed you how to play around with the values of filling the pipe and but never go on the positive side. But how negative can we go? And how close can we get? It said approximately 11.1. Well, we'll never get it that close, but just to show you that we have this tool called Piper that you could ask some of these questions, and you say, oh yeah, what is it the value that I want to use? And I put these in long before David. I looked over his slides and I thought, well, knowing David and the kind of questions and the presentations he does, I know what to ask, or show. And here's the thing again, what is a typical value for longitudinal compressive stresses in an HD? And of course, it'll go through the whole process here of it's not explicitly stated in the documents, but however, if you take it a little bit further, the maximum shear stress is typically 45% of the specified minimum yield strength, and then we could take it a little bit further. This calculation is essential for ensuring the stresses imposed on the pipe. Do you see the benefit of something like this? This is what Piper does. It says what happens when the max allowable shear stress of 45% is less than the max shear stress. Well, we're in trouble. Okay, so I just want to point out that when the maximum allowable shear stress value of the SMICE is less than the maximum stress experienced by the pipeline, it indicates a potential failure condition. I'm not going to read all this stuff, but the point I want to point out is that Piper gives you some of the things that we can't always cover in detail. David goes into a lot of detail and he covers them in his classes. But what if we forget? What if we don't remember all that stuff? Well, it's going to show up in somewhere in with Piper. And then it says what are the benefits and differences, and why would I want to purchase HDD? Well, I'm not going to spend time on this, but this is Piper's uh, answer. But let's take it a little further than just a question like that. here we have applications and so on why you would purchase it. But let's ask the question, what are the benefits between bore aid, that's the driller's tool, versus HDDPT? And that's the question you should ask, because we already know your HDD, the power tool, is the one to use. Advanced design insight, cost reduction, and so on and so forth, comprehensive calculations. So, but bore aid, is for more simplified calculations. What the big difference is, why would you choose? In summary, because we have all of these other calculations that David went over in detail, especially with the frac out, which or what we call the borehole stability, and that's what we're talking about. David mentioned some of this stuff, and this is what he's talking about. When the minimum mud pressure exceeds the maximum mud pressure, what do we do? And this is what it's all about. And he pointed this out over and over again, how important it is to get these things right, your soils. And this is why I brought something like this up, because I thought it was important. And so yes, there is a driller's tool, but there's also, if you want more complex situations, when David mentioned a compound bends and things of this nature, it does it for you. These are the kind of this is what makes the difference between other tools out there and the tools here. And I'm not telling you this. Artificial intelligence is telling you this. So I'm neutral on this. So, but I asked the question anyhow, and then we ask what's the unity check? And that was the last thing I think David ended up with. David, I don't know how I read your mind on a lot of this stuff, but this is the kind of thing, we want to. It's the combined stresses, as David said, and why do we want to look at this? Because this is we want to understand what we're doing. And how could we understand? So we could look it up through Piper, our artificial intelligence, and give you the calculations. Do we have the calculations somewhere else? Obviously we do, because up here we have a question mark, and you could get that same information, but it's a lot simpler when you go and ask Piper the question, and he'll give the answers real quickly. It says the unity check ensures that the combined stress is less than 1.0, and the safe bending or hoop stress in all regimes, whether it's plastic, elastic, and the transition. So it explains all of these things. And I don't know if you guys recognized, when David ran the pull force calculation. Let me take this down one more. We give you what the tensile strength is, the bending and so on, but David ran the pull force, and I don't know if you noticed it, but it'll analyze your results. It'll tell you if you passed and how much you passed or failed. And this is why I brought this up, because if you noticed, when David was showing it on the right hand side of the screen, this came on, and you could run all these calculations each time, and this is what makes the difference of why you passed or why you failed, and some of the background behind it. So this is what I wanted to bring about Piper. And one other thing I wanted to bring out was the sensitivity analysis. You could do sensitivity analysis on mud weights and things of this nature. You could make your comparisons and do things, and then you have the option to do study plots, mud weight, and so on and so forth. You have a lot of options here, to take different points and so on and so forth. So I offer this. I just wanted to offer this, as another tool in the tool chest to make your job easier. And Kesley, I turn it over to you for the next phase of it. Okay.
Perfect. Thank you so much, Joe. And just to answer, I know I saw this already pop up once or twice in the question section. While we're still on this Piper screen, just to answer what I think a few of y'all are asking and thinking, Piper does search inside Technical Toolboxes knowledge base, but it does not, and also verified sources as far as regulations, code, PHMSA, anything related to that. But it does not use outside sources such as random website searches like Google would do. So everything that it is Piper and Piper Insights is pulling from is a verified source, whether that's through our knowledge base related to our products or verified sources related to regulations, codes, and things in the industry, trusted sources. So just so you know, everything is verified. It's not like your typical Google AI search.
Thank you. Thank you, Kesley. That's a good
Yeah,
backup.
absolutely. So we're going to run one quick poll question, and then we're going to get to some of these Q&A. We have so many. I'm just going to go ahead and let you know we are not going to be able to cover all these. So if we are not able to answer your questions that you submitted live, please know that we will follow up after the webinar via email, whether that some of y'all have multi-part questions that we will probably schedule a call with you just to go over all the answers, but the rest we will answer via email before the end of the week. So please know that we will get back to you as soon as possible if we can't cover it on the webinar. While this poll question has another 30 seconds to run, David, I'm going to start asking you some of these questions that were submitted so that we can get to them. So some of these are multi-part, so I'll start with this one. David, if we encounter any existing underground clashes that we cannot avoid along the chosen drill profile, does it also consider horizontal steering left or right to avoid that clash?
If you encounter any underground clashes,
Yes, sir. So I guess related to the power tool, if they have some type of underground barrier or clash, can we avoid that along the drill profile, steering left or right?
well, if you have room to avoid it, I mean, assuming you know it's there when you do your layout, you could avoid it. Now, if you're doing drilling and then you're going to, you don't know it till you hit it, of course, then that's too late then. But if you're talking about doing your investigation, you identify something you want to avoid, and can you do a left or a right turn to avoid that? Yes, you can. And the one I showed you had a compound bend. You can also do one that just has a left turn or a horizontal bend. You can make it right turn or left turn. So in the power tool, you can do straight sections, you can do curves, you can do compound bends, you can do horizontal bends, and you can do vertical bends. So whatever you need to do to negotiate that obstacle, that you can load that in the power tool to get the calculations.
Perfect. Okay, another part to this question. Does the tool also perform the drill design for HDPE pipeline? And is there a maximum depth limit for the drill profile of the HDPE pipe?
Yes, I didn't show you that the module I showed you was steel. There's another module in the power tool that does plastic pipe, polyethylene pipe, and it'll same way. It'll do it in any plane you want to do it in, and it doesn't have a maximum depth as a number, but it does calculate the loads on that pipe. And again, if you exceeded the allowable external hoop on that, then you get a fail just like you do with the steel.
Perfect, thank you. Okay, for the HDD borehole stability tool, okay, so the borehole stability within the HDD power tool, can you confirm the unit weight of soil in the calculator refers to the total unit weight as opposed to wet/submerged?
Yes, the weight that you put, if you remember that table I showed you, if you go back to my slide, you'll see that it had on there. Let me. Are y'all seeing my slide, Kesley?
Yes, sir. You can go ahead and scroll. We can see you scrolling there.
If you go right here, this soil unit right here, you see it's got total and submerged, and so most time when you get it, you'll get the weight of the soil, and then you'll get the weight of the water. That's going to be your total weight, and the submerged weight is just the weight of that soil. So in the model, when it asks for the weight, it's asking for the total weight. Is what it's asking for. it actually calculates the submerged weight based on the water weight. So it uses the standard value for water weight, 63 point, whatever it is. Unless you're in salt water, then you can tell that you're in salt water. Use that weight there.
Perfect. Thank you, David, for showing us that. Okay, here's another one. So, does the toolbox verify and conduct calculations for the delamination check against the soil force on the barrier HDPE pipe during the pullback process to avoid damage to the external coating of the barrier HDPE water pipe? It's a mouthful.
Yeah. Read that one more time.
Yeah, no worries.
What kind of pipe? HDPE?
Yes, so does this
Okay.
toolbox verify and conduct calculations for the delamination check against the soil force on the barrier HDPE pipe during the pullback process to avoid damage to the external coating of the barrier HDPE water pipe?
No, I mean, there's no calculations that check for delamination. Now, uh, if you're pulling in your high density polyethylene plastic pipe, again, you typically don't have a coating on that. And that does calculate the pull loads on the pipe and the stress, but it doesn't calculate any type of coating stress for steel or plastic or anything else.
Perfect. And I know we're over time, but I'm trying to get to as many of these questions as possible. So here's another one for you, David. If the soil is very soft and can't maintain the borehole, still do we do HDD, or is this the primary check for feasibility?
Well, no, if the soil was very soft, like I showed you, if it's very soft at the surface, then you can. Normally, what we'll do is we'll use that conductor pipe that I showed you a picture of right here. So normally, when you go up and you see that conductor pipe at the surface points, entry and exit, that's because we had very loose soils at the surface. And I've had to drive those in 300 feet to get down to dense enough soils to work in. So that's you can do that. But normally we'll drive those down to wherever we have to go to get down to a dense enough soil that we can support the hull. So it doesn't make it a showstopper, but it is something you have to address.
Perfect. Okay, let's see. There's so many I'm trying to sort through here. Here's a good one for you, David. What is a typical range for drill angles? What are the risks that would be encountered for an aggressive drill angle?
Okay, normally on the entry side where the drill rig is, normally we'll try to go somewhere around 12 degrees going into the ground. That's just a rule of thumb. Ain't nothing wrong with that. As the soil gets stiffer, gets harder, then we'll get a steeper angle to make sure we penetrate the soil. And a lot of time, if you hit, I mean, if I got a rock ledge down here, then we'll make it even a steeper angle, maybe something like 14 or 16. And we'll get that steeper angle because we want to hit that rock at more of a direct angle. It helps us penetrate the rock. Okay, so we never go less than 12, and we'll go up to 14, 16. If you remember that picture I showed you, where was it at? Oops, right here. See, you notice this right here? That's up. If I remember, that was about a 24-degree angle, something like that. Again, and the reason they did that is because they had to make depth real quick. So if you have to make depth real quick, you can go with a steeper angle. But your angle is limited by the rig and what you can do, and of course, whatever soil conditions you're going to use to help get in there. But as a general rule, 12 degrees. Then we'll go up steeper if we have to get through rock, or if we have to make depth real quick. The problem with the steep angles, now that's on the entry side. On the pullback side, 8 degrees is usually what we'll use for most pipes. And then the bigger the pipe gets in diameter, the smaller you want that to be. Because remember that pipe, when it comes up, when just say you come up out of the hole at 8 degrees, well, the contractor has to pick that pipe up and get it coming back down that hole at 8 degrees. So the steeper this angle is right here, the higher he's got to pick that up to get down that hole, which is going to increase your risk of stress. Okay. So normally, the bigger the pipe gets, we're going to make that angle get less and less. If I'm looking, I'm talking steel pipe now. If I'm looking at a 16, 20 inch above pipe, I'm going to get down around 4-degree angle just to make it easier to pick that pipe up and get it down that hole. Now, if you got plastic pipe, again, it's a lot more flexible. You can pick it up a lot more and get it down the hole, so you can go steeper angles with that. But normally we'll go 12 in, around 8 out. As the pipe gets bigger than say 8, we'll start going down from 8 to 6 to 4 and get down lower. Now, what do you pay for having those steep angles? Remember, whatever angle you go down at, whatever angle that is, when you start that point of curvature, you've got to make that bend to get back to horizontal and come back up. The steeper this angle is right here, the longer that arc's going to be, and the deeper you're going to get here. So it takes a lot more room to recover from those steep angles. So don't get any. That's why normally 12 is a good starting point, and 8 is a good starting point.
Awesome. Thank you, David. Okay, last question before we close out. I know we didn't cover everyone's questions. We will follow up via email after this webinar. So last question for you, David. Are there recommendations for supporting the pipe during pullback, understanding that rollers and cradles will be used throughout the process? My question is primarily associated with limiting stresses that the pipe would be subject to throughout the process.
Yes, well, normally during pullback, that goes back to what I just showed you. In fact, we have what we call canonary, and again, I covered that in detail in several of my webinars, and I don't have a slide real quick to show you, but what canonary is, if this is where I'm coming out of the hole right here, and I calculate how much we got to pick that up and come down, and so this right here is called the catenary. And we calculate how high you got to pick it up and how long this has to be without overstressing that pipe. Now, we base this arc here usually on the 100 diameter rule. So whatever diameter the pipe is, we multiply it by 100. So let's say it's an 8-inch pipe. I would have this right here, an 800-foot arc, 800-foot radius. I mean, arc is what we've been. We use that 100D rule. And we use that, we'll calculate that height and that length. Now, we'll calculate what we call the bending stress to that pipe. And we do it the same way you calculate the allowable spanning distance for any above ground pipe. If you were in a reg station or a meter station or whatever, we have those calculations based on the weight of the pipe and the length of the span, what that spanning distance is. And we calculate that and we give that to the contractor in our specs. And just say we tell them, okay, any elevated pipe has to be supported at least every 40 feet because of spanning stress. So what the contractor will do in his pick plan, he'll have rollers out here, and he'll have them at least every 50 feet. Most contractors, if you tell them 50, they would have those rollers about 40 feet apart, because out in the field things get moved around, get kicked. He don't want to overstress the pipe, but he would have those rollers about whatever you told him that distance was. Now up here, he's going to have a support every 40 feet, but it's going to be a backhoe or a crane, whatever he's using to pick that pipe up and support it, but it'll be every 40 feet as well, okay? So all that's based on not overstressing that pipe, being able to pick it up and get it down the hole. The higher he has to pick this up, that's why that canonary is so important. We never tell a contractor what his pick plan is. He does that. But I do want to know, my angle right here has a big impact on that pick plan, because the steeper that angle, the higher he's got to pick it up. And once he has to pick it up more than, say, 12, 15 feet, then he has to start using cranes and things of that nature, and they get a lot more expensive because it really increase the cost of your drill. So it's called a pick plan. It's part of what we call the canonary plan. And the spanning is based on typical pipe spanning distance, and then the height and the length based on that catenary.
Awesome. Thank you so much, David. And thank you, Joe, also. Thank you all for submitting your questions. Again, for those that we didn't address live, we will follow up via email. You will also all receive a recording of this webinar via email, and it'll be made available on our YouTube channel before the end of the week. Special thanks to David Willoughby and Joe Pikas for the presentation and the demos, and to everyone in attendance. If you have additional questions or interest in something in particular that we covered or maybe didn't cover today, please reach out to us. Like David and Joe both mentioned, they offer training courses related to HDD, but many other topics as well, AC interference, pipeline toolbox, as well as just other industry training is available through Technical Toolboxes. So please reach out. Our contact information is shown here, or please request a demo on our website. Again, thank you all, and we hope you have a great day.
Thank you.